And I'm going to work a few of these factoring problems, let you guys look at them, and then we'll go from there. You guys keep commenting any questions you have of any specific ones so we can go over those. I'm going to start with number 4. If I had 10a to the second minus 5a to the fourth, the first thing I always look for when I'm factoring is there a GCF? So I have two terms. 10a to the second is a term. Negative 5a to the fourth is a term. And so the way I explain it is each term has different parts. So this has the number part, which is called the coefficient, and then it has one variable raised to the second power. And then same thing here. This term has a coefficient and a variable part, a to the fourth. So first, what's the GCF of the coefficients? I think most of you guys can probably do this. 10 and 5, the GCF would be 5. So we would factor a 5 out. And then it's just division, right? So 10 divided by your GCF of 5 gives 2. And then 5 divided by 5 gives 1. So we're going to write the 1 this time. But normally, if it's a 1 and you have more parts of the term, you can just ignore that part. But we'll put the 1 there for now. And so I've got the coefficient part of the GCF finished. Now, we want to look at the variable part. So they both have an a. The first one is a to the second. So the way I think about that is that's a second. I'm doing a bad job. Sorry, it's been a minute since I've done this. Just ignore it. Just ignore that part. So I have a to the second and a to the fourth. So what is the highest power that they both have in common? And so what I was trying to explain before is, I imagine this as being like two buildings. A to the second and a to the fourth. The first term has 2 floors. The second building has 4 floors. Because one to the second, one to the fourth. So what's the highest floor that we can get to in both variables, in both terms? Because they want to wave at each other. Well, this guy goes to the second floor. Well, this guy, he can't go any higher than the second floor. He's got to stay there. Because if he goes up higher, you won't be able to see him. So a to the second is all they have in common. So I'm going to factor that out. And so if I had a to the second here and I factored an a to the second out, then that is a to the 0, and a to the 0 is just 1. So we could write times 1. I'm just going to leave that part out. Then I've got the minus here. And again, a to the fourth has a GCF of a to the second. So what we do here, we subtract exponents, right? So if this is 4, and I took 2 of them out, 4 minus 2 is 2. So this is the factored form of number 4. 5a squared times 2 minus 1a squared. Or we could write that as 5a squared times 2 minus a squared. This is where I was talking about you don't have to have that leading 1. Either way, we're good. All right, let's work number 10. 10 is similar in that we have 2 terms and we're looking for a GCF. But your exponents have now gotten a lot uglier, right? So let's go there. I got 2 terms. I have a coefficient and I have a variable part. So when I look at the number part, 2 and 3, there's not any factors they have in common. So we have to factor out a 1 for the coefficient part, meaning the first term still has a 2, the second term still has a 3. Now they both have an x, so we can definitely factor an x out. But now what's the highest floor that I can get to that they both share in common? Well, if you look here, they have an n part and a number part. So what's the highest n they have in common? This one goes all the way to 2n. This one only goes to 1n. So the highest floor that we can get to in both of them is just 1n, meaning I'm going to factor an n out. And then look at the number part that's after it, the whole number without a variable. This one goes to 3. This one goes to 1. So the highest that they have in common is 1. So I'm going to factor out an n plus 1. So your GCF here is x to the n plus 1. So if I factor out an n plus 1, remember it's like subtraction. This one went to 2n, but I got one of the n's out. So how many n's are left? Only one n is left. And then this one went to 3, but I got 1 out. So 3 minus 1 is 2. And then looking here, this one only goes to x to the n plus 1. And look what I factored out. I factored an x to the n plus 1 out. So n minus n cancels, and the 1 plus 1 cancels, meaning this one has no x part left. And so this would be my final answer right here. Yeah, let's just leave it at that. I don't want to confuse you anymore. All right, let's do a couple more. These are the difficult ones for the GCF, 12 and 13. First thing, when I look at 12, it looks awful because I've got fractions. But it looks even worse because this one is a mixed number. So the first thing I want to do, I never want to do math with a mixed number. It's just weird. So I'm going to turn this mixed number into an improper fraction. So this is a good review for some of you guys that haven't done this in a long time. How do we convert mixed numbers to improper fractions? You take the whole number part, which is 1, multiply by the denominator, which is 7. So 1 times 7 is 7. Add the numerator, which is 7 plus 3 is 10. Meaning I could rewrite this as 2/7 x to the third plus 6/7 x to the fifth minus 10/7 x to the fourth. And now that looks much cleaner to me to find the GCF. So now I've got 3 terms, but all 3 terms only have 2 parts. I have a coefficient and I have a variable part. The variable part you guys probably don't think is that difficult here. X to the third, x to the fifth, x to the fourth. What's the highest floor they all have in common? It would be x to the third, right? And so the trickier one here is these fractions, 2/7, 6/7, and 10/7. If it helps you, because they all have a common denominator, I could go ahead and factor out that 7th. And just once the 7th is gone, I could just kind of ignore it here for a second. So now, what's the numerators? 2, 6, and 10. So what would be the GCF of 2, 6, and 10? Well, they're all even, so the GCF would be 2. So we would factor out a 2 in the numerator. So for 2/7, 6/7, and 10/7, the GCF would be 2/7, x to the third. So now then, if I took 2/7 x to the third out, 2/7 x to the third, and I took out 2/7 x to the third, there's nothing left of the first term, meaning I have to put a 1 as a placeholder. I know earlier I told you you could ignore the 1. Well, that's as long as you have a variable and other parts of that term. But when the whole term is the GCF, I have to put a placeholder for a 1. Now what happens here to the 6/7? 6/7, but I took out 2/7. Well, this is just division. We'll just, again, we took the 7th out. You could just kind of ignore that. 6 divided by 2 leaves me with 3. This would be 3, and I had x to the third taken out of x to the fifth. Means I subtract that to give me x to the second. And then same thing here, 10. But I took out 2, so divide. 10 divided by 2 is 5. And then x to the fourth, but I took out x to the third. Leaves me with x to the first, or just x, which is here. All right, and the last one's with radicals. The nice thing is they both have a radical, so I can just keep that the way it is. Again, you're probably not going to have any issue with the variable part. X to the fourth and x to the third gives an GCF of x to the third, meaning this is going to be x minus, and then the x part of the second one is gone, right? So that's nice. But now I have radical 5 and 10, radical 10. So if I'm taking the GCF of this, because they're both under radical, I could just act like the radical's not there and just put it out here. So if you had to take the GCF of 5 and 10, the GCF would be 5. So the GCF of radical 5 and radical 10 would be radical 5. So this used to be a radical 5, but I took out a radical 5. So what would be left? A 1, which again, we don't have to put it this time because there's already an x. But it's okay if we do. And then I have a radical 10, but I take out a radical 5. So this is just division. 10 divided by 5 is 2, meaning what I have left is radical 2 for 13. All right, nobody asked about this one. I do want to point out here that number 6 has a misprint. I'm pretty sure that this should be an X and not an S. Sorry about that. And there was a misprint on the first one as well, the first section, number 11. Just ignore that. Just don't even do that problem. It's not worth it. So, factoring by grouping. Nobody sent me a question about this section, so I'm assuming we did okay on it. But anytime you have 4 terms, the first thing I'm looking is, can I factor by grouping? So I'm going to do number 3. The way we group them, we group the first 2 terms together and the last 2 terms together. And then it's just find the GCF of each group. So if I look at the first one, AC and AD, what do they have in common? It's an A. Factor an A out, that leaves me with C plus D. Now for the second group, BC and DB, they both have a B, so B is my GCF. If I factor a B out, it leaves me with C plus D. Now for grouping to work, the parentheses must match. The parentheses do match. Check the box. We did good. I'll explain more of this later if you guys have questions. I'm just going to tell you kind of what you have to do. Because the parentheses match, I just put the parentheses as the first part, and then what's in front of the parentheses is your second set of parentheses for it to factor. So A times C plus D plus B times C plus D factors to be what's in front of the parentheses, A plus B, times the matching parentheses, C plus D. And you'll hear me say it like that over and over. I'm not going to work any more on this one because you guys didn't ask me to. But yeah, if you have questions on those, just let me know. Okay, looking at the difference of squares section. You've asked me about 3, 7, and 8. So I'm going to work each of those, even though I think you might be a little bit disappointed in 3. 3 is similar to 2. And the fact is you can't factor that. So why can you not factor 2? Because this is addition. This is a difference of squares. I can't do anything with a sum of squares. So that one's not factorable. All I want you to write is prime. Number 3 is a difference. That's good. Theta to the second is a perfect square, but 11 is not. So because that's not a perfect square, I can't factor it. So it's also prime. Okay. So yeah, those are kind of weird. Number 5, you would need to rearrange it to put the negative in the middle to make it a difference. And let's look at number 7. So when I look at 7, it doesn't jump off the page as me as a perfect square because this is an odd exponent. And to be a perfect square, it has to be an even exponent. So I'm already thinking there's a little trick here. There's something they're wanting me to do. Well, remember, the first thing we always look for when we factor is there a GCF? So on number 7, there are 2 terms, but they both have an R. So I can factor the R out. If I take an R out of R to the 5th, that leaves me with R to the 4th. They don't have an S in common, so S to the 4th stays. If I take an R out of RT to the 6th, then the R is gone. It's canceled, and we're left with just T to the 6th. So again, GCF was R. Now look what's in parentheses. I have a difference. All of these exponents are even. This exponent is even, meaning it's a difference of perfect squares. So now I can factor what's in parentheses to be the square root of the first term. So I just divide by 2 the exponents. The square root of the square root of the first term and the square root of the first term here as well. The square root of the second term is t to the third and t to the third. And then for a difference of squares, we alternate the signs between them. One is positive, one is negative. Just don't forget you have an r here. And so this is now factored for 7. All right, another one that was asked was number 8. So let's work on 8. So this is a difference of 2 terms. So are they all perfect squares? Well, let's look at the exponents first. A to the 4th, that's even, so that's a perfect square. B to the 10th is even, so that's a perfect square. So we're good with the variables and the exponents. 121 is a perfect square. It's 11 times 11. What about 4/9? You probably don't know fraction perfect squares very well, but all you got to know is the numerator a perfect square? It is. Is the denominator a perfect square? It is. So you just take the square root of the numerator and the denominator independently, and it actually works out to be the same. So this is a difference of perfect squares. So what's the square root of the first term? Well, the square root of 4 is 2. The square root of 9 is 3. The square root of a to the 4th is a to the 2nd. The square root of the second term, the square root of 121 is 11. The square root of b to the 10th is b to the 5th. We just divide by 2. And then alternate the signs. One of them is positive. One of them is negative. Should use a different color. And so that would be the answer for 8. Now let's look at 4. These are weird. Like, you probably never seen anything like this before. And you're not going to see it very often. But it's just good to know you can do that. So this is still a difference of perfect squares because all of this is in parentheses. So we just treat this as a term. It's a perfect square because it's raised to the second power. 36 is a perfect square because it's 6 times 6. So whenever I'm doing the difference of perfect squares, it factors to be, what's the square root of the first parentheses? Well, x plus 1 squared will just be x plus 1 and x plus 1. What's the square root of 36? It's 6 and 6. And then we alternate the signs. One is positive, one is negative. And all of these, you can see, they're all just like this. All right, they're just going to look a little funny. But you're not having to do anything else besides factor it. So this is all we need to know how to do. You can do that for all of these. If you have questions on one specifically, just let me know. All right, number 5, this is one we want to turn into a difference of squares, but it's not currently a difference of squares. So what we do here is we're going to find 3 terms that are alike and that are what we call perfect square trinomials. Sometimes people come to me and call them Jesus problems. You won't hear me use that terminology, but if that's what you want to think of, this is a perfect square trinomial because the first term is a perfect square. The second term is a perfect square. Or it's not second. I'm a moron. First term is a perfect square. The last term is a perfect square. All right, well, the square root of x squared is x. The square root of 9 is 3. And if we multiply x times 3 times 2, and it's always just times 2. All right, that's standard. The square root of the first, the square root of the last, times 2. That would give me 6x. That's the middle term. So if that happens, it is a perfect square trinomial, which means I know this factors to be x plus 3 times x plus 3, which we can write as x plus 3 squared. And then that's leaving me with, I've not done anything with this minus 25y squared. I just bring it down. And now you'll notice this looks just like the problems above it. So it's a difference of perfect squares. So this would factor to be the square root of the first is x plus 3. The square root of the last is 5y. And then we're going to alternate the signs. One's positive, one's negative. So again, these are also very strange and just weird. But it's good to practice all of these things. It gives you some new techniques. It helps you practice some pretty difficult factoring. And just know that we won't do any factoring during the year that is quite this difficult. Right? This is as hard of factoring as we'll do. So we're just challenging you, seeing what you can do here, and showing you some new techniques. Kind of get you thinking outside the box, which is a good thing. So yeah, if you have any questions on any of those, send them to me. I'll work whatever. And then the last section here is difference of cubes, and some of them are also sum of cubes. So there are two formulas for sum of cubes and difference of cubes. A cubed plus b cubed, and a cubed minus b cubed. You may not have ever seen these, or you may have done it in Algebra 2. I don't really remember. We don't see it a lot in pre-cal, but we can see it occasionally. So for the sum of cubes, a cubed plus b cubed is a plus b times a squared minus ab plus b squared. And then for a difference of cubes, it's very similar, except this is now subtraction, and this one's now addition. Okay, so if I'm just going to work one, let's work, I'll work 3. So this is the difference of perfect cubes, which would be this second formula. How do I know it's a difference? Because there's subtraction between them. And this is a perfect cube. X to the third is x times x times x. So that means I know my a term is x. And now then the b term, 8 is also a perfect cube because it's 2 times 2 times 2 is 8. So my b term here would be 2. And so I'm just going to take x and 2 and plug them into the formula below. This becomes x minus 2 times x squared plus x times 2, or 2x, and then b squared. That would be 2 squared. 2 squared is 4. And so this would be my final answer for number 3. If you have any of those specific questions, just send them to me as well.